Time to graph the trig functions. You may have seen that sine and cosine graph as waves. In this video, we'll look at why that happens. We'll look at the sine function first. For graphing, we'll use the unit circle definition of the trig functions. We can always consider the input x as a radian angle, but for present purposes, we'll think of it as any real number, and it corresponds to an arc length distance along the unit circle. Recall that the output of the sine function is the y value from the location on the circle. Before we start drawing the sine graph, note that its x-axis is not measuring the same values as the x-axis that the unit circle is residing on, even though both axes are labeled x. The x values for the graph we are about to draw come from the arc length measurements on the circle. The y values, however, do match in this case, since the output of the sine function is the height of the location on the circle. In effect, the distance along the circle gets mapped to the x-axis on our sine graph. For the moment, we'll just worry about one full revolution around the circle. Since the circumference of the circle is 2 pi, that gives us a span along the x-axis of our new graph of 2 pi. For our graph, it's helpful to measure the x-axis using increments of pi rather than integers like 1, 2, 3. Let's see what a few points will look like. If we start at 0 arc length on a unit circle, our height is 0. As we proceed around the circle through quadrant 1, the heights of our locations increase to a maximum value of 1. This corresponding arc length is pi over 2. Now we continue through quadrant 2, with the heights decreasing back to 0 as we approach the arc length of pi. In quadrant 3, our y values turn negative and approach negative 1 as we end the quadrant at an arc length of 3 pi over 2. Finally, we move through quadrant 4, with our y values approaching 0 as we return to our starting point. You can now see the wave taking shape. The 4 quadrants from the circle create 4 distinct sections of the sine wave, corresponding to the rises and falls through positive and negative values. Notice that the graph is steepest when the arc lengths are measured at the left and right edges of the circle, as that is where the y values change most rapidly. When we look at the top and bottom points of the circle, the y values change very slowly, and the sine wave almost flattens out. We have drawn one complete wave shape of the sine graph, but the graph is periodic, meaning that it starts repeating the same shape. The period, which is the length of one full cycle before it repeats, is 2 pi. If we continue our rotation around the circle, the wave will extend. If we measure arc lengths clockwise, the wave extends to the left, corresponding to negative input values. Notice that although the complete graph extends infinitely to the left and right, the y values always stay between negative 1 and 1. This is because they correspond to coordinates from the unit circle, and the unit circle never extends beyond 1 or negative 1. We say that the amplitude of the wave is 1, which is measured from the vertical center of the wave to either the highest or lowest points. Here is a way you can visualize how the shape of the sine wave is formed. Suppose you are watching a friend riding on a Ferris wheel. As the wheel revolves, you are tracking the height of the chair over time. You are ignoring the horizontal movements of the chair. You just watch the vertical changes. Now graph your height observations with time on the horizontal axis. You'll get a perfect sine wave shape. The amazing thing about this graph shape is how often it appears in nature. We drew it by tracking the heights as we go around a circle, yet this shape matches the rising and falling tides of the ocean, the phases of the moon, the number of hours of daylight throughout the year, the vibrations of sound waves. the many wave phenomena from physics like light waves and gamma rays and X-rays and microwaves, and many, many more.